is Dr. Chris Milczynski. He's an associate professor at Syracuse University, and he would be talking to us on a topic that is going to complement in a different way what has been going on today on formal methods for software security. Before I let Chris start speaking, I have to tell you when I met him and how he ended up giving a talk today. Chris visited us here at Pullman very recently, and I attended his talk. He was talking about data log that I didn't know very much about, but there were very interesting connections with graph algorithms and scientific computing that I have done. And it was a fascinating, wonderful talk. And after that, we chatted, and then I told him, we have this workshop going on. I really liked what you did with this, and I wanted to have some formal methods on software security to be addressing our summer workshop. And then I gave him a warning. Your audience is going to be undergraduate students. They are interested in security. That's why they are here. Are you going to be able to deliver a talk that they would understand? And he was ready up for the challenge. And he said, no, I actually enjoy doing that. And so that's how he's joining us from where he is now. I'm very delighted that he took the time to talk to us today. Chris, when you are ready, you can go ahead. And the screen is up and everything is ready. Please go ahead. Welcome.
Hi there, everyone. So I hope you're all doing well. I'll be, if you want to interrupt with questions, that's fine. But we can also save the questions to the end. Since I'm remote, that might be easier too. So maybe if there's something that's very confusing, feel free to jump in. But otherwise, I'll just be kind of moving forward and we can have some extended discussion. I probably won't use the whole time. And I will kind of prefix my talk by saying this is kind of a mix of material from various, talks and classes I've given on this topic over the years. Some of the material will be very intuitive. Some of it might feel a little bit more advanced. So there's no need to understand everything here. If there's more advanced material, it will be followed up with more intuitive material at the end. So hopefully if there are points where you feel like you're getting lost, there will be some hooks to get back in, and then we can have kind of a discussion at the end of the high-level message. I think there's a pretty intuitive high-level message here, even if you don't get 100% of the, technical content, let's say. So thanks so much for having me. A little bit of background about myself. As Asaf said, I'm an associate professor at Syracuse University. I've been here for, 8 years now. And my work is in programming languages. I do basically analysis of programs to validate them for various security relevant components. So that might mean automatic exploit identification. So like you give me a binary, can I find an exploit in it by using whatever method? These days, AI is a very popular aspect to do that, for example. But AI is complemented by some of the methods that I'll be talking about today. Or maybe something like you want to prove the security of a program. And that was a problem I've been thinking about a bunch over the last years. And I will give some of the ideas for how we solve that in this talk. So, okay, the talk at a high level, the goal of the talk is to sell you on the idea of using formal methods for security. So what are formal methods and why would we care about them in the context of security? So the issue is just that many concepts from security are quite nuanced. So what does it mean for a program to be secure? Or what does it mean for a program to leak sensitive information, right? The issue, and this is something that we're going to be able to see by the end of the talk, but the issue is that it's not a functional correctness property. So what's a functional correctness property? A functional correctness property is something where you can write out a test case that says there's a bug or there's not a bug, right? Most of the time when we're doing programming, we can write a little test case that says the program either got it right or it got it wrong. Security does not work like that, and that's why it's so hard. And the reason is that to be able to articulate whether a program has a security bug or not requires us to reason over more than just a single run of a program. And this is a very deep idea that I will try to convey throughout this talk. And we'll try to see exactly in what way is that true. But the basic issue boils down to the fact that you really can't be precise about what, security even is until you have a threat model or until you have an attack model, right? And this is just a reality of life. All statements that you can make that are security statements, they're really only correct up to some attack model. So the idea of formal methods is that we can use mathematical logic to make statements about a program's security, and that enables us to be rigorous. It enables us to be precise, right? Otherwise, all we have are kind of hazy statements that are just about, things we might suppose would be true, right? Or things we might argue to somebody in plain English would be true. But how can we actually believe whether they're true or not? To do that, we really want to use mathematical reasoning and especially mathematical logic to be able to reason about the program's security. And so that's really the basis for what we're trying to do in formal methods, is that we would like to be able to give you a convincing and rigorous proof of a program's correctness by using mathematically founded reasoning to do that. But the issue is just that there's no way to do that unless you fix a threat model. Okay, so here's a little example of an application. It's not secure, and I'm interested in you kind of brainstorming a little bit how. I won't solicit input from everyone here, but just think about it for a little bit. So we've got a web app. It allows logins with a username and password. And if you log in successfully, it takes you into the main page. You see your, information and maybe a dashboard. But if you fail the login attempt, it returns you back to the main login page and you can reattempt. And all usernames and passwords have some finite length. Let's say whatever it is, it's in characters, maybe, let's say 100, whatever you pick, right? And the question is the app secure in principle? And I would argue it's not. It's not secure in principle. And the reason is that the app actually, it implicitly leaks whether the password was correct, right? And so the attack is you can just try all possible passwords. Now, that might be practically quite hard, right? So for example, if the password length is n, then you might be trying some exponential space of inputs. And so that might be very hard in the sense that if you make n very large, you could make it impossibly hard, right? You could make it to the point where you'd have to try more combinations of atoms in the universe, but maybe you can exploit some information like, the password is actually less than 12 characters or, just any possible thing you might infer about their password. But in the limit, the app is not secure in principle, because if you had an oracle that could just hammer on the server, right? Like if you were a government nation state that was willing to set up tons of different password attempts, well, then eventually you could crack it. And in fact, big governments and security organizations have lots of compute at their disposal. And if they need to read encrypted data, it's not impossible for them to just literally try tons and tons of passwords. But of course, if the password is quite long, then that's very tough. Like, for example, a SHA key or something like that. So this is an example of an app that, it's in a violation of this thing called information flow that we'll be discussing more in depth. But you can see even in this kind of a common application, it's not easy to solve the problem, right? And so what does that mean practically? So practically what that means is that you would want to institute something like a lockout policy, where maybe on a per IP basis, you only allow somebody to have 3 or 4 attempts maybe, or some limited number of attempts. And then if you saw that they were trying to log in too frequently, you would need to ban their IP. And then maybe they move to a different IP, right? Because maybe it's a big government that has access to lots of compute resources. So then you might have a policy like, well, if a user's account has more than whatever, let's say 50 attempts from different IPs, you just shut it out and say that you have to have the user get in contact with maybe a trusted authority to provide something like a physical ID or some other third party kind of out of band mechanism. And that might help you prevent serious loss of data and information integrity from this kind of an attack. So that might be the practical upshot for why this violation of the app in principle, how you might secure it in practice. But my point is just that even in this simple example, which is one that we see all the time, right? I mean, we all use these kinds of portals and things like that. Many of them do have kind of password lockouts. And it's because of this kind of reasoning. It's already nuanced just with this example. So what about this example here? So I have this function read int, and I've got some pseudocode here. I'll be writing in a bunch of pseudocode, which is just kind of no specific programming language, but you can probably figure out what it means. So here I read two secret inputs. Whenever I read an input, I have to tell you whether it's secret or not, but we're just going to assume the input coming in from the keyboard here is going to be secret by default. And here's what I do. I read a secret integer, then I read another secret integer, and then I sum them up, and I put that into x, and then I say y is equal to x minus x, and then output y. And the answer in this case is that the app is non-interfering, which means it's, so that's one definition of security. The reason it's secure is that in this case, it always outputs 0. So no matter what the inputs 0 and 1 are, we take their sum, but then we subtract x from x, that always gives us 0. So if we're somebody standing on the other end of the application, we're only ever seeing 0 no matter what the inputs are. And that makes this app non-interfering, something we'll talk about later. But you might say, okay, so in that setting, the security model is you can't see the secret inputs, but you can see maybe the outputs. And of course, to make this rigorous and firm, we have to be even more thoughtful about really pinning down all those details. But even here, it kind of depends on the attack model. So maybe an ultra aggressive attacker, what if, for example, you're somebody like the NSA who has the ability to command Amazon Web Services to be able to give you fine-grained access to a machine and see clock cycle level timing? Well, if you can see clock cycle level timing, you might know on modern architectures that, for example, the plus operation doesn't always take the same amount of time. It might vary depending on what these inputs are. And so if you're a very motivated attacker, you might be able to learn something about, for example, even the timing of various inputs could tell you a lot of information. And so that's called a side channel. We'll talk about that a little bit towards the end of the talk, but in general, side channels are very tricky and they're very tough things to observe. But the point of the talk is just that trying to make these definitions rigorous is really the only way we can really get our heads around them formally. Here's another example. So I have a bunch of examples. I think these are kind of the most important part of the talk to see. The talk will become more technically complex as we go, and I'll kind of skip through sides as it seems relevant. But I figure giving some good examples can really help us. So let's look at an example here. I've got these two inputs that I'm reading from the keyboard, and I'm going to assume they're both trusted, like secret inputs. And so I have input 0 is read int, and then input 1 is read int, and then I set this variable x to be 0, and then I say if input 0 is less than input 1, set x to be 1. But otherwise, don't set it to be 1, leaving it at 0. And then at the end, I output x. And my question is the app secure now? And of course, I haven't defined what security means. We're going to try to get there by the end of the talk. But the answer is basically no. And the reason is that you can observe a difference of the app's behavior depending on the configuration of the secret inputs. And so the app actually here, we leak the fact that either the first input is less than the second or not less than the second, right? If we look at the output and we see 0, we know that it wasn't the case that input 0 was less than input 1. If we see 1, we know it was the case that input 0 was less than input 1. And one of the most interesting things here is that we never directly copied any secret somewhere. So we never took input 0 and input 1 and copied them into X, for example, which is a way that you might try to fight security and things like that and data flow. One of the things we'll look at first. So this is basically leaking. It's not leaking the whole output, or sorry, the whole input, right? But we are leaking basically a predicate or a decision on the input. And we might call this a bit, right? In computer science, a bit means a single 0 or 1 value. A bit is essentially something like a binary yes, no decision. And in this case, the program leaks basically 1 bit of data. It leaks 1 decision, yes, no of the input, not the whole input, right? Maybe if you could repeatedly run this program, you could leak more, but at least some of it. And so in principle, this application is not going to be considered secure, where this one might be. Assuming that you can't see timings, you only look at outputs, you only ever see the output 0. Well, that program is the kind of thing that's not going to have its behavior influenced by the secret inputs, where this one does. Namely, it leaks whether the input is less than, the first input is less than the second. So what do formal methods have to say about these programs, right? We've been talking about them intuitively, but what can we say formally about them? So the reason that we care about formal methods for these sort of settings is that reasoning about security is clearly a little bit tricky. And in fact, we can't even be precise. We can't even be, we can't even really nail down what we want to say unless we have an attack model in mind. So what things is the attacker allowed to observe, for example? Is the attacker allowed to observe just the outputs of the program? Can they observe the outputs and also the timing that it takes? Can they observe maybe the internal state of the machine? Like, for example, the power usage, right? You might imagine that even if you couldn't discern anything from the outputs, if you were able to see that the machine was using more power, for example, that might tell you about how it was executing, right? And so this whole, nuance here motivates applying these formal methods. And formal methods are mathematically rigorous, sound reasoning to programs that help understand their security. And there's generally 2 kinds of things we can do, right? So when we talk about formal methods, there's kind of a dichotomy between what's called testing, right? So testing is basically you can see when a bug occurs, and that's different than verification, which is being able to prove that there's no way a bug could ever occur. And the first is basically an existential statement. It says there exists some program for which the program has an exploit, or there's some input for which the program has an exploit. The second is stronger. It says for any input and for every circumstance, there will never be a security exploit. And so this is a general thing that happens in computer science. There's a difference between testing and verification. Verification is more powerful than testing. And why is that? Well, it's because in verification, we're trying to make a for-all argument. We're trying to say that for any input, we can prove to you or verify to you that there will never be a crash, or in this case, a security vulnerability, which is our kind of crash. So that's kind of where the dichotomy breaks down in formal methods. We're going to ask, what does it take in this talk to verify the security of a program? How might we try to get our heads around that? How might we do it? So we're going to talk about several different approaches to formal methods for security. I'm going to focus on one, program analysis, which is going to tee up some of the talks, I think, later in the CySER workshop later on. I know my collaborator, Tom Gilray, is also giving a talk where he'll discuss some program analysis as well. So program analysis asks this question of basically, I give you a program, and you tell me, is the program secure? And so it's like, I've got a program that's existing, and I have a technique, in my case, program analysis, which can look over the program and can approximate definite behavior of the program. So this is something like, I wrote the program, and I want to know, is it secure or not? That's different than security type systems, another way of verifying programs for information flow security or their various security properties. So with a type system, The type system is really more something that we don't apply to a program post hoc. It's something that we apply to a program sort of as we're constructing it. So the type system will reject programs that would be offensive. Now, type systems have their own set of constraints. We're not really going to talk about them too much here, but I'll point them out as a different approach, just as sort of a difference from program analysis. There's also program logics. And so there's lots of different ways for reasoning about formal methods. Another one is called a program logic. And a program logic basically allows me to take the program and based on the program, write out a set of constraints. And if I can solve those constraints, that constitutes a bug. I can basically take that set of constraints and a solution to the set of constraints demonstrates a bug. Or if I can prove that the constraints are unsatisfiable, meaning there's no solution to the constraints, then that helps rule out a bug. So, these are three different mechanisms for ruling about, sort of reasoning about program security. We won't talk about all of them. We'll talk about some of them. But these are different. My point is just that there's lots of different ways to reason about a program's correctness. And many of those mechanisms for reasoning about program correctness have often been leveraged to also reasoning about security as well. So if we want to reason about a program, we need some way of specifying its semantics, right? Because if I don't have a semantics for the program, if I don't have a mathematical representation of its meaning, then I can't have any hope at being able to use mathematics to, reason about its security, right? So for example, what I mean is that I need some abstraction of how the program executes and some mathematical abstraction, right? So, it might be enough to just say, oh, well, the program's meaning is just whatever the Python interpreter says, right? Well, that's fine if I just care about executing the program. But if I actually want to reason about the program, I need to have something more mathematically rigorous than that. And so one way I might do it, and this is the way I'm going to, mostly talk about during the talk, is that a program's behavior is basically an input-output trace, right? So here I've got a trace that outputs 0, outputs 1, outputs 2, outputs 3, doesn't ever take any input. So this would be a program that just outputs a whole bunch of, a big stream of numbers that are increasingly going up to infinity, let's say. Then I've got this program over here, it inputs 0, and then it outputs 0. Was that because I input 0 or not? Well, I'm not really sure. We'll get to that later. It may or may not be the case that that's true. Kind of looks like it here, but we don't know quite yet with only seeing this one trace. Then I input 1 and I output 1, keep going. So that's an example of a program that's interleaving inputs with outputs. And then here in this program, it just outputs 0 and then it stops. So these might be three different traces for a program. And we might say that the program semantics is actually the set of all possible input-output streams associated with the program. So that's going to be roughly our presentation of the program semantics for the purposes of this discussion. When we actually want to pin down all of these definitions, we need to be more rigorous about, for our specific language and our specific model, what is it going to be? But this trace-based model is a pretty common one that will work for a lot of these definitions. So one of the most basic ways that I might try to verify a program's security is by using something called data flow. So data flow analysis is basically a mechanism that I can use to track how data flows from inputs in my program through intermediate data in the program. Like for example, see here I have x is equal to read input. So I'm reading an input from the console. And then I'm saying the variable y, it starts out as being equal to 0. But then I'm taking y and I'm adding x to y. And so because x is sort of a secret input, I can think here that now x kind of flows to y. And now y has become sort of, we'll see on the next slide, there's a mechanism for what's called taint tracking. But I can sort of see that the data from x has flowed to y because I'm combining x and y by using plus. And so by bundling up the secret data x with y by using plus and putting that in y, well, now I've kind of captured some of the secret data in X in Y. And then when I output it, it flows to my output. And so if I used a data flow analysis, this program would be rejected and would be called insecure. And there are methods of doing this that are based on runtime, right? So there are, for example, if you're using a language like Python or Ruby or various other languages, you can often find versions of those languages that have what are called dynamic taint tracking. And so what happens there is that those are basically runtime enforcement mechanisms that will make sure that if you read in secret data, it becomes kind of annotated with a source of what's called taint, or just some label that says, hey, this is actually sensitive data. And so here on the second line, y is equal to 0. So that's not tainted because 0 is not something that comes from a secret input. So no problem there. But then on this third line, we add y to x. And because x is tainted, the taint propagates from this computation y to x to y, because we're writing into y as an output. And then at this point here, when we output y, because y has been tainted by using it and bundling it up with x by adding it, because it's been tainted, when we try to output it to a public source, well, then the dynamic reference monitor, right, because this is sort of a dynamic mechanism that's running at the same time of the program in this sort of a setting, well, at that point, the program would crash. And we would say, no, you're not actually allowed to output y because it has been tainted by the secret input x. So that's something called taint tracking, dynamic taint tracking in general. Actually, taint tracking can either be static or dynamic. So if it's dynamic, what that means is that it's sort of like dynamic typing, right? Programming languages with dynamic types are determined at runtime based on how you use them. And a type error occurs when you use a program and, when you use some piece of data in an incorrect manner. It's a very similar thing here. Dynamic taint tracking propagates taint at runtime, which, by the way, incurs overhead, because now you're paying an additional runtime overhead to also do this taint tracking. You've got to have some space where you're storing, these taint annotations. And then also, as you're propagating data, you've got to be propagating this taintedness as well. And then also, you have to be checking and possibly crashing the program if there's a bad scenario. And so this is kind of like testing in the sense that you can observe bad behavior whenever you observe this violation of tainted data getting printed out to tainted output. And it's not just, printing out to the console. It's also doing things like writing to disk or sending out network packets or anything else like that. So that's dynamic taint tracking. And dynamic taint tracking is kind of nice, but unfortunately, it's not actually sufficient to guarantee the freedom of security violations. So we'll see why later on in the talk. I have a lot of slides, but many of these slides I'll be skipping through and just covering the relevant ones for the stuff I'm saying here to just kind of modulate my time. But this is an important concept because even people in industry use things like dynamic taint tracking to check whether programs, propagate secret data to outputs. And the issue is that, first of all, as we're going to see, it's not really fully secure. There are situations where the program doesn't violate this dynamic taint thing, but it still is in violation morally of the security property. You can also do what's called static taint tracking. So in static taint tracking, you analyze the program at compile time, and what you do is instead of reasoning over just a dynamic run, basically at runtime tracking this stuff, what you're doing is you're actually reasoning over all possible runs of the program using something called static analysis. And this can help you ensure that there's no possible misuse of data. And this is more powerful because rather than just being sort of reactive at runtime, it's actually proactive and tells you at compile time that no, actually, we can prove that there's no way of hitting a runtime error. And so this is kind of more like verification in the sense that you can prove the absence of bad behavior. And to actually reason about this, you do something called static program analysis. So static program analysis is this idea that we can compute finite approximations of a program's behavior, which might be infinite, right? A program generally has an infinite number of inputs. And so the goal with static analysis is to basically take the program, look at just a finite, do some finite amount of computation on it, and from that finite amount of computation, be able to tell you that definitely it will do things either in a secure manner or it could potentially be insecure. And so static analysis is a requirement if you want to make sound judgments. So what I mean by sound judgments is basically for all statements. If you want to be able to say, okay, well, the program over any possible input will be free from some bug, in this case, a security violation, you really need to be doing something like this, which is a very heavyweight statement because it tells you about all possible behaviors of the program rather than just being reactive at runtime to identifying things that go wrong when you see them go wrong, right? There are also some other downtime sides to having things be tracked at runtime. First, the overhead, like I said, but also just the fact that in general, we don't really want our programs just randomly crashing, right? That's kind of an unfortunate reality, but in production, we would really prefer not for the program just to randomly crash sometimes and have to have our engineers go look and figure out why is the program crashing due to the security failure. It would be much nicer if we had the ability to be able to soundly say, no, we can run the program without this extra, heavyweight infrastructure and know that it's in fact going to satisfy the security policy. And these ideas of static program analysis actually go back to somebody named Gary Kildall, who was actually one of the original creators of the MS-DOS system. There's an interesting story about Gary Kildall that I'll let you look up, but in my recollection of the events, he basically was kind of swindled out of some of his money by Bill Gates and ended up having a very tragic, ended up having this very tragic accident in a Corvette, as I recall. So there's some interesting history here, but he was the person who invented program analysis as a field, and he invented it in the context of being able to reason about programs in the process of compiling them. And so he had this paper from 1973 that spawned this whole field of static program analysis. In this kind of program analysis, we're doing what's called data flow analysis. And data flow analysis is a specific kind of static analysis that approximates how data flows through the program. So if we look at this program here, we can see I've got this expression b plus c, and I'm using it twice. So I'm using it right here, and I'm using it right here. Now, that's a little bit naive. I shouldn't have to calculate b plus c twice, because between the calculation of b plus c right here and the recalculation of b plus c right here, I haven't changed either b or c. So instead, what I could do is I could just say, okay, we'll just calculate it once and call it an intermediate variable. And then I can use it here and then right here. I don't have to calculate it twice, but over down here, I might have to because the definition might change, for example. And so this is a kind of analysis. I can solve this by using something called an available expression analysis. And this was one of the original kinds of static analyses, original kind of data flow analyses that Gary Kildall developed. One of the things that goes into this is that what's going to happen is you're going to have to now, because you're reasoning over all possible paths through the program, you have to wonder, what happens when, for example, at a certain point in the program, I might have multiple paths that are converging. So here I've got a complex program where I've got a loop header, and the loop header is going to jump into the body, or when the loop is done, it's going to jump out to the end. And at the end of the loop, I'm going to go back to the header to retest the guard. So that's how guards work, is that at every point, I'm testing whether the guard is true. If it's false, then I go to the end of the loop to continue the rest of the program. But if the guard is true, I go back into the body of the loop and re-execute it again. And so to consider and handle a loop, I have to be able to handle the fact that, well, to consider all the different possible infinite runs of the program, I have to be able to collapse those no matter how I came from them. And so I have this thing called a join point. And so at a join point, I merge my analysis results. In this case, my analysis results, so the things that the analysis are calculating, it's calculating a set of, in this case, it's available expression analysis. So it's calculating a set of definitely available expressions, of expressions which have been calculated, but whose contents have not changed in the intervening times. Let's see, I'm going to start skipping through sort of some stuff here, but just sort of saying that available expressions analysis is an instance of a common class of data flow analysis problems where the analysis results are a set of facts, so some set of things that you might say about the programs. The set of all possible facts has to be finite because I need for my analysis to be able to terminate. In this style of analysis, each statement in the program is going to be associated with a set of analysis facts which get generated by the statement, and also things which get killed or invalidated by the statement. And then when I have different paths in the program merging together, I'm going to combine them. Because they're sets, I'm going to combine them with either union or intersection. And so if I think about, well, I've got two different ways of getting to this point in the program, I'm going to take my analysis facts and I might, for example, union or intersect them up to be able to reason about that. And this leads to a set of standard intra-procedural data flow analyses. Intra-procedural just means within a single function, right? So inter-procedural means reasoning across functions in the program. But if I can make it easier just by doing what's called intra-procedural data flow analysis, which is just reasoning within a function, and I have this class of analyses that were defined by Kildall. Reaching definitions is sort of what variable definition is live at what certain point. I've also got live variables, available expressions, and very busy expressions. And this has been systematized in a framework called abstract interpretation. And in this framework, you kind of make things more formal and rigorous by arguing about the termination of the analysis by using what are called monotonic functions. These are functions, so a function is monotonic when it's only going in one direction or only ever adding information. And so you can think of these things as requiring something like something called a lattice. So this is a term that I'll just point out. You don't have to know the definition for the purposes here, but I'll just say a lattice is a mathematical structure that allows us to order information. And so a lattice consists of a set of lattice elements. In this case, it might be something like analysis results, like secret information from variable X flows to this point in the program. Might be an example of analysis results. And then we need to be able to order analysis results using a partial order, which relates elements. And that relation is reflexive in the sense that anything is related to itself. Antisymmetric, so antisymmetry means if X is less than Y and Y is less than X, then X and Y are equal. And then it's transitive. If X is less than Y, or sorry, less than or equal to Y, and if Y is less than or equal to Z, then X is less than or equal to Z. And lattices also give us the ability to join up information. So if I want to merge information, lattices will let me do that. They'll also let me meet information, so finding sort of the lowest bound of information. And then I can take the set of all information and no information. And so these are used in being able to generalize these data flow analysis results. But even this is not so good in the sense that if we want to be able to reason over all possible runs of a program, we need to be able to know what happens between functions in a program, right? So if I have a large program, for example, like this program here, so the issue might be, so this program contains a bug. Well, it might contain a bug, let's say, because here I call the function f with -1, and then I'm dividing 1 by f. So this is a potential for a crash if f returns 0. So the question is, does it return 0? And so there are a few different ways of reasoning about the program. One might be sort of be a coarse way where I just sort of conflate all possible outputs from f. And I might just say, okay, well, here I call f and it contains -1. right? And so then that goes f negative 1 returns x plus 1, so that gives me 0. And then if f returns 0, well, then that's not good because I step into this point right here and I get a crash. But if I think about it, when I call f with negative 1, 0 is the result, and so that's never going to be equal to 1, and so this branch is going to be skipped over. And so if I know that this branch definitely fires, then I know that this branch has an error. But if I'm not being thoughtful about it, one thing I might do to make the analysis simpler is I might just say, well, just conflate all the different outputs from f. So I might look at all different calls to f in the program. So I see this call with negative 1 here returns 0 because negative 1 plus 1 is 0. But if I look at this call here, when I call f0, I actually get 1 because f applied on 0 yields 0 plus 1, and that gives me 1. So if I'm being, if I'm being coarse about it and I don't differentiate the positions in which f are called, I might just say, well, both 0 and 1 are return values from f, and you need to consider either of them. And that's what this lattice idea sort of gives us, is the ability to conflate multiple results in a way that still lets us kind of gracefully degrade down the set of behaviors. So if I do that, then I get this false positive that spuriously tells me, well, the result could either be 0 or 1, and in fact 1 is equal to 1, so to be pedantic, I need to consider the fact that maybe there is a crash here. But if I'm more fine-grained about it and I analyze f on what's called a context-sensitive basis, meaning I differentiate the behavior of f at the different points where f is called, I can see that in fact, no, this guard will never be satisfiable because f on negative 1 yields 0 and 0 is not equal to 1, and so this potential bug will never actually be triggered. But doing that context-sensitive analysis is, for many reasons, a little bit more expensive than, well, quite a bit more expensive than the context-insensitive analysis. Okay, so that was data flow analysis. And data flow analysis is a compiler-directed mechanism and sort of a mechanism for reasoning about the program and understanding how data propagates through the program using sort of mathematically inspired formalization. And I'll put up, I'll send my slides out, so if you're interested in seeing more of the details, you can go deeper into the slides. And if you're interested in really learning the material, I have a bunch of information in a compilers class that I have that relates to some of this. But one of the things that I said earlier in the talk is that data flow analysis is not sufficient to be able to rule out all bugs. And so I have an example here of this one that we've just discussed a little bit earlier, something called an implicit flow. So if I use data flow analysis, here I would say, okay, well, the secret data flows to input 0. And then here the secret data flows to input 1. And then x is equal to 0, and then I branch here, and then I set x is equal to 1, and I look at x, and now x, well, there's no apparent problem. And the reason is that there was never any data flow from the secret inputs over here to x. And so x only had, the 0 value, which is from the program, or the 1 value, which is from the program. And by default, I would probably assume that the program source is public, right? That's a pretty common thing because, even if the program is, secret, maybe it's closed source, well, you can always do something like reverse engineer it, decompile it, or something like that. Or maybe you get a leaked copy of it because maybe some employee, leaks out a copy of the code. So in general, we would say that the program, constant values from the program are public. And so if I look at this program and I use data flow analysis would tell me that this program is fine because the only things that flow into x are the constants 0 or 1. But in fact, if you think about this program a little bit, you can see that in fact it does reveal a bit of the input, or the inputs, I guess I should say. It's a relationship between the inputs. So this is an example of something called an implicit flow. So there's an implicit flow of the data input 0 and input 1 to the output, x. And the implicit flow is something that data flow and thus taint tracking will never find. So even if you use, for example, taint tracking to be able to try to secure this program, it will not prevent this kind of a leak. And so this topic is called non-interference. So static analysis handles the data flow, but it's not sufficient to ensure this non-interference property. Just to state non-interference semi-formally, because I don't have time for a fully formal definition, but in non-interference, which is a very heavy-handed security model, my threat model is going to be programs, inputs, and outputs consist of high security and low security portions. And you can also make this more granular by talking about multi-level security, like maybe low security, medium security, and high security, or even more fine-grained than that if you're interested in that. But this high security, low security dichotomy is enough to set up the basic definition. So if we have a program P, I'm going to say that the program P is non-interfering if for every two inputs, input 0 and input 1, if input 0 and input 1 are low equivalent, meaning if I look at just the public portions of I0 and I1, then the output of the program that is predicated on that input I0 had better be low equivalent to the output I1 for all possible inputs I0 and I1. So I had better be able to take any pair of inputs, I0 and I1, and if they are low equivalent, then the output had better be low equivalent. And if you think about this and scratch your head a little bit about it, what you realize is that basically this is saying there had better be no way to be able to discern any low observable difference, no matter how I change up the high security inputs. So if I take the high security inputs and twiddle them a little bit or change them a little bit, that had better not be able to lead to any low observable difference. Because if I had a low observable difference, if I looked, if I looked only at the low observable outputs of the program and I saw them varying, well, then I would know that depended on a high security input. And that would be a violation of this non-interference property. So this is actually a very complex property. In fact, it's not even a property of a program. A property of a program is something where I can take a trace, a single trace of the program, and I can tell you whether the program satisfied the property or not. So that's something called functional correctness. So this property, non-interference, is not actually a property of a single trace of a program. It's something called a hyperproperty. A hyperproperty is something that depends on sets of traces of the program. And this is generally the class of security statements made in formal kind of rigorous security definitions. These hyperproperties were introduced by Michael Clarkson and Fred Schneider at Cornell University, and they really set out the kind of the outset of how do you get your head around these kinds of formal definitions. So let's look at some. So here I've got my high security inputs. In this case, I'm just assuming the input is high security, and I'm assuming the output is low security. Now, to actually set up the threat model, I have to tell you what's high security and what's low security. I'm just going to tell you in this case, the input is high security, the output is low security. So let's look at this input over here. Let's look at this program over here, which is violating non-interference. It violates non-interference because it leaks whether input 0 was greater than 5. It's kind of a variation of the earlier program we looked at. If I see a 1, I know that input 0 is greater than 5. I don't know exactly what value it's equal to. I don't know that it's equal to, 6. I don't know that it's equal to 7, but I do know something about it, right? So non-interference is a very strong property because it tells me something about the secret input. And this is the way in which the password example from the very beginning of the talk is also non-interfering. Because if I get the password right, then I see that the page went through successfully. If I get it wrong, I see the try again page. So if I look at all the possible traces of this program, I have traces like input 0, output 0, input 5, output 0, right? Because 5 is not less than 5. If I did less than or equal to, it would output 1, but as is, it just outputs 0. But then once it becomes 6, well, now I'm suddenly greater than 5, so I output 1. If it's 7, well, I'm still greater than 5, so I output 1. And so if I look at all of these different or low security outputs, I see some of them are 0, but some of them are 1. But if the program is to be non-interfering, these or low security outputs can't depend on this high security input. So this program is not secure from the perspective of information flow. Where this program over here is secure in the sense that if I look, so let's see, here input 0 is greater than 5, I output 0. Else, I output 0. So this is kind of not a very good example. It's a little bit artificial, right? Because the program is not very useful. But this is an example of one that does satisfy non-interference, because no matter what the high security input, the output is always 0. So by looking at the output, I'm never actually seeing or learning anything about the input. So I can see non-interference as kind of, when do I learn information about the output? So non-interference is a very strong security property, and a variety of methods exist to reason about it. So security type systems, program logics, static analyses, dynamic analyses. Let's say that I want to fix the static analysis idea to reason about this, or taint tracking. Is there a way that I can do it? And the answer is yes. What I can do is I can basically track another piece of data, which I'm going to call the program counter. And the program counter is going to be an upper bound on the current context of all branches performed by the program. So when I branch, so here I'm doing an if comparison, right? So that's a branch. So when I branch on high security data, what I'm going to do is I'm going to say, well, now the program counter is going to be high security because I've branched on high security data. When I've made a decision based on high security data, I'm going to up the security of that program counter. And now, if my output is public, well, I'm going to say, no, you are in a branch that depends on high security data. So by outputting right now, what you're doing is you're outputting based on high security data, and that's no good. And so if I retrofit my taint tracking with the ability to track the program counter, well, now all of a sudden, I can start to track information flow. Although I would say that program, taint tracking, would still complain about this program. It would say this program is also rejected, when in fact this program would be correct according to information flow, because this program always outputs 0. Taint tracking would still say, no, you branched on a high security output, or a high security input, so you can't make any output right now. And so in that mechanism, it's very hard to both be precise while also being correct. And that's an interesting thing here. And I'll just end my talk. I'm concluding here. I'm just going to end my talk by saying even this notion of information flow that depends on program inputs and outputs, even that is not enough. And so let's look at this new setting. So here's my program. I'm going to say input 0 is equal to readint. Now let's say if input 0 is greater than 5, then sleep for 100 seconds. Otherwise, do nothing. And regardless of what happens, output 0. Now, according to the definition that I just gave of non-interference, this program is non-interfering. And the reason is that the output is always 0, no matter how I vary up the input. But if you can watch the timing of the program, then you can see, well, if the input 0 is greater than 5, it's going to wait 100 seconds and then output. Maybe I'm on the other side of a network channel. And so I just see, oh, well, the server waited 100 seconds and then it sent me the input 0 back. But if immediately it sends the input 0 back, I know that input 0 is not greater than 5. And so side channels are very tricky to reason about. And this is a place where we can see the breakdown of the security setting start to crop up. And so just in summary, I would say, security definitions are very tricky. Whether a program is secure or not depends on the attack or threat model, right? So what does the threat model encompass? Does it encompass power usage, timing channels, control flow, or maybe just outputs? You might, for example, like a big way in which people break cryptographic ciphers, let me tell you, this is a very interesting part, is they are able to identify ways in which cryptographic code is implemented that will do things like, do implicit branching based on certain bits of the input, right? If so, when we write cryptographic code, we have to be very careful to make sure that the execution paths are always constant, no matter what the secret key is. To any degree that we might observe different timings based on the secret key, that would be a violation of information flow. And so often, this is why we basically tell students never write your own crypto library. Even if you get the crypto correct with respect to the output, right? Even if you do encrypt the output correctly, you might reveal some portions of the input just by things like timing channels. And those are very hard to rule out on modern CPUs. For example, if you've seen the meltdown attack, that relates to, for example, how the CPU caches secret data. And then data could be either present or not in the cache, making it take different times. So just to summarize, formal methods give us a high degree of rigor. And, many of us look at rigor and just see pedantry. But the reason that we really need rigor in the case of security is that these statements are so nuanced that they really require mathematical precision to be able to get any degree of, correctness about them. And it's not enough just to track, data flow. We also have to consider things like information flow, timing channels, and other things like that. So I appreciate your time. I'll wrap up there, and I'm happy to take a question or two, time permitting, but I appreciate your time. I think the room is still muted for what it's worth. Yeah, the Zoom is muted if anyone's asking questions.
All right, I'll wait. Ah, that's what, Chris, that's one of the things you had missed. There was an enthusiastic clapping from the students for the talk. So
Well,
that's
I appreciate that.
yeah,
Thank you,
and
students.
we are headed about towards lunch, so we can at least be able to take quick questions because
Wait, may I
nobody's
ask
speaking.
one question?
Yes.
Sure.
So are all the methods that you went over today manual?
No, mostly not anymore, especially.
Because I was gonna
Mostly,
ask like your opinion on automated testing and like how you think that's beneficial to like more sensitive data and larger data sets.
sure. Yeah. So I would say, yeah, so there's a few ways, right? So first of all, automated testing in the form of fuzzing has been extremely popular for catching security bugs. So people used to do fuzzing quite a bit to find security vulnerabilities, and you can build fuzzers that can detect violations of information flow and data flow and all sorts of stuff like that, and it will work. Um, I would also say even methods for proving the correctness of programs, even if they could be done manually, you can also do things like get modern generative AI tools like, Claude Code and the latest frontier level models and loops with agents. You can get rid of a lot of the manual burden that we were previously seeing by using advanced generative AI. And there's a robust industry of people who are applying these advanced methods in ways that would have been very hard for a human to do, just because they're very tedious to write out all the proofs and things like that. They're applying the logic-defined reasoning about the program using modern generative AI to be able to have a heyday. And I think this is one thing that will become more and more relevant over time because modern generative AI will accelerate the ability of finding security vulnerabilities, right? You can imagine most people and nation states and things like that will be using advanced models like Mythos and stuff like that to find bugs in programs. But also by the same time, people will be using those methods to actually perform formal verification showing a lack of bugs. But of course, part of my message is the lack of bugs is only correct up to a security, like a threat model. And so one of the things that's most exciting about security is just that you can always shift the definition based on the threat model. So if you prove a program is secure, you can always, the key is just change the threat model up and find a way in which it's not secure under some different threat model. But I definitely think, modern AI tools will be hugely kind of change the game in terms of how this kind of work happens. Even aside from all of the good automated efforts like buzzing and proof search and things like that that were already helping that even before generative AI came into the game.
Thank you very much. Anybody has any other quick question? So, Chris, you had correctly said there is a speaker, Tom Gilray, will be speaking tomorrow on program analysis. And you have also nicely tied side channel attacks, which was a topic that was talked about just before you, and some crypto stuff in the morning. So we are very grateful that you took the time to talk. You anticipated that I was going to ask about your slides. If you want to reduce them and send us fewer, that's great. If you want to send us the whole thing, that would also be awesome. So whatever you choose, please send us so we can put it on our website. And we're headed for lunch. Thank you very much again, Chris.
Thank you all and have a good lunch.